Hey guys, welcome to another video. So today we're going to start a new topic in the Extension 1, Year 12, or Year 11, Year 12 actually, syllabus of vectors. Now, as part of vectors, you learn a few things. Obviously, you start off with defining things like the magnitude, dot products, etc. But I thought we'd do a few videos on possibly the hardest part or the harder part of vectors in the Extension 1 topic, and that's the component relating to geometric proofs. Now, the thing about geometric proofs is in 3-unit and 4-unit, it's part of the syllabus. So one way a teacher at school can make the topic harder in 3-unit in Extension 1 is to throw in Extension 2 quality questions. There is no defined difference, right, between the geometric proofs in 3 and 4-unit. I think it's just the intensity. So yeah, so today let's start off the process of some typical questions, and you'll see the typical questions today we're going to do broadly covers things like proving things with right angles and proving parallelograms, etc. Very typical. You'll see it in you see it commonly in exams, in trial papers and topic tests. So I'll deal with a few just to introduce the framework. Next lesson, we'll possibly do things with ratios of sides, collinear points, etc. And maybe I'll do another video at the end, so 3 videos, the third video covering harder questions or just longer type questions with more marks. So that's the plan. Hope you like these videos. If you haven't already done so, please subscribe to the channel, like the video, share it with your friends. Get them watching these if it helps with their learning. So let's get started. So I'm going to start off this video just by painting the picture of vectors, geometric proofs. So with geometric proofs, a lot of those questions sort of utilize the same sort of concept. Now, whenever you hear whenever you use or hear things to do that relate to right angles, right, or proving something with 90 degrees, we know that in vectors, very commonly, if they sort of are perpendicular, meet at right angles, cut each other at 90 degrees, let's say this vector is u and this vector is v, we're going to use dot products, right? That is quintessential as part of this topic. So I always say to my students, whenever you're dealing with this, 99.9% of the times, whenever you hear the words prove these vectors are perpendicular, prove that it meets at right, you're going to be using dot product, right? It is the most common thing to use. Another very common thing to use is that when you have dot product of the same vector equaling, when you have the same product, that gives you the magnitude squared. That's very useful for proofs that involves where they give you sides are equal. Normally when sides are equal, to relate it back to dot products, you're going to use this fact. The last thing I want to talk about is whenever you try to prove parallelogram, right? So for parallelograms to be proven in this topic, there's a number of ways to do it. The most common way that they do, right, is to basically say and prove that 2 vectors are equal. So if I said to you, this is AB, let's say, and let's say this is CD, to prove that ABDC is a parallelogram, all you really need is AB as a vector equal to CD. Now, I say to my students, this sounds quite simplistic, but what's embedded, right? What is implicit in this statement, once you've proven this, is that 2 things, right? Whenever 2 vectors are equal, it implies that they are parallel. AB as a line, as an interval, is parallel to CD, right? But not only that, whenever you prove 2 vectors are equal, it implies that their magnitudes are equal, right? Which basically means, as an interval, AB as a length equals to CD. And once you've proven that, it's a parallelogram, right? Because you have a pair of parallel and equal sides. So with this sort of easy framework to start with, and we're going to do a number of past paper questions that have this sort of, that utilizes this part of the theory. So now, some of these questions, for those that don't know, right, and you're new to, I guess, studying this topic, in the New South Wales syllabus, vectors has only been introduced for 2 years, since 2020. And so what that means is that since 2020, there's 2020 and 2021 past papers, trial papers that have these types of questions. So this is not a lot, right? What you may not know is that, across all of Australia and potentially in the world, right? But I'm only focused in Australia. Say, for example, Victoria. Victoria have had vectors as part of their senior syllabus for 20 years, more than 20 years, right? So you'll see some questions. In fact, the first question I'll show you from the VCE, which is the equivalent of the HSC, in 2001, that's where the past paper came from. So past paper question we'll start with. So I guess what I'm trying to say, there's a whole rich history of vectors in past papers in Victoria that we can draw on, right? And so just to let you know that the past paper questions that I'll deal with transcends the New South Wales history, right? Because it's only 2 years. Let's dig past back all the way to the VCE. So let's get started. So where's my question? There it is. So from the VCE, first question we have is quite simplistic, right? So we have a question that has a triangle, 3 equal sides given there. Let's see, what are they asking me to do here? In triangle ABD, AC, okay, these 3 sides are given to be equal. Let, right, AC, where's AC? Over here, this guy here, equal to U. Let BC, so this one coming up here, equal to V. Perfect, right? Use the vector to prove. Now, there you go, right? The moment you see, prove that that's a right angle, this guy is telling you, right? Where's BAD? This guy here, right? The way I would do it is potentially prove that BC as it meets AD, that dot product, right, is equal to 0. So if I can prove that BA, let's say BC, I meant BA, dot product with AD is equal to 0, then it's a right angle. That's the proof, right? So I say to my students, whenever you see that dot product equals 0, that's the key. So, and then all you're trying to do, guys, is basically now try to express the green vectors of BA and AD in terms of the blue. That's really what you're trying to do, right? Utilizing the facts given. Now, you can see because they're equal, this vector here is also V. Now, why did that give you the lengths are equal? Because they're basically, this guy here, this fact here, is telling you that the magnitudes are equal, right? The magnitude of U equals to the magnitude of V. Now, given that, we're going to use some dot products to basically prove that the green dot products are equal. And the way we're going to do it is by using sum of vectors. So let's explore the top triangle first. So the top triangle sort of looks like this, right? We've got 2 vectors, one going this way, one going this way. We know that this guy's U, this guy's V, and just to label the vertices, this is D, this is A, this is C. I can see from this diagram, right, by observation that the vector AD, the green vector, equals to AC plus CD, which equals to U plus V, right? Piece of cake. Right? Tick. Let's explore the other green one now. So I got one coming backwards, and I got one going upwards here. And I got one coming downward, upwards here as well. So that's V, and that's U. All right. Now, so let me label the vertices again, B, C, A. So in this one, the green, I want to make green resultant, which means I'm going to reverse, right? Reverse the order of this guy to make it negative U. So then, in this case, BA would equal to V minus U, right? Pretty straightforward. Once you do that, right, I need to demonstrate that the dot products equals 0. So therefore, if I said BA dot product with AD, right, that's this guy times this guy. So V, sorry, when I say times, I mean dot, right? So don't treat it like binomial expansion. Although, algebraically it is. The only difference is when you expand this using your rainbows, right? Yeah, you just it's not v vector squared, it's v dot v, which is the modulus, sorry, modulus, that's 4 unit, the magnitude squared. So this one's v dot v, right? Please don't write it as v squared. That's not a thing. So that one, sorry, well, I don't know why I started with the VV. So I should be starting with VU plus VV minus UU, and then minus UV. Now, because they're equivalent, this guy will, wrong one, this guy will cancel out this one. And we know, right? We know that V dot V, as part of our first page, that's the magnitude of V squared minus U magnitude squared. And because the lengths are equal, right, you can sort of say that that's the same as V minus, sorry, U minus U, right? Because V equals U, which equals 0. Perfect, right? Very simplistic proof. I suspect this is worth 3 marks, 1 mark for top, right? 1 mark for this bit, 1 mark for this bit, and potentially 1 mark for here, or maybe a half mark to 2 top ones, and then 2 marks downstairs. But there you go. Once you prove that, the dot product 0, therefore, angle BAD is a right angle. Piece of cake. So, very straightforward from the VCE 2001. Questions like this has been sort of replicated over time, and you'll see more and more of the Victorian questions being replicated in the New South Wales one. So yeah, let's do a few. So I think the next one is from the New South Wales syllabus. So from the Catholic school papers, we have a question from 2020 from, that looks like this: 2 marks. ABC is a parallelogram. If AB equals to BC, AB equals to BC equals, right? We're talking lengths here, right? So why this? Because this guy equals to this guy, right? I'm going to probably use the magnitudes there. Prove that the vectors AC and BD are perpendicular. So once again, there's that word perpendicular, right? The moment you hear about perpendicular, we're basically saying that prove that AC dot product with BD equals 0, right? So then your challenge really is to express, where's AC? Down here. Where's BD? Over here. Express those 2 green as a function of all the other guys. So for example, if I let this guy here be A or U, maybe U, and I let, now it doesn't matter which direction you go, because eventually it doesn't matter. Let's say this guy be V. All right, by this fact over here, right, that's telling me, right, that the magnitudes are equal. Now, then my aim, just like the last question, I'm going to try to make those green vectors in terms of the blue, use dot products. That'll take me to the end. Actually, very similar in terms of what we got now. Because this is a parallelogram, we know that the opposite sides are equal in vector form. That's V as well. Given that, guys, quite simple. Like, you can sort of see it there, right? That this green one here, the first green one here, BD, right? This one here is equal to V plus U, right? So maybe I'll just go there. So DB, right? Directionally matters. DB equals to V plus U. The order doesn't matter. You can do U plus V if that floats your boat. And then this one going downwards. Now that's U and then minus V, right? So it's 2 marks. So I guess we can skip that. So AC equals to U minus V. And then you go, therefore, AC dot product with DB equals to, and then we do exactly what we did before, right? Exactly what we did before. Can you see the pattern? The algebra is repeated in so many questions, right? And this is what I say to my students. Once you sort of realize this is the game, right? Whenever you deal with this perpendicular perpendicular type of question, and you talk about dot product equals 0, it's predictable. Yeah. So if questions in vector geometric proofs are predictable and tedious, that's amazing, right? That's where you want to be, right? Because predictable in a 3-unit test and tedious is good, right? That's a good sign. So, you know, it's a good way to getting easy marks, so you can focus on the harder stuff. So once you get there, guys, predictable, that gone, and there you have it again, where you get that's magnitude squared minus magnitude squared, and we know that they're equal. So I'm just going to replace the v, the v with the u, which gives me 0, right? Done. Yeah, then once again, therefore, prove that the vectors are perpendicular. So AC, it's gonna, I always repeat the question when I'm proving it. So are perpendicular, right? Is that all right? So 2 marks there. Now, how many marks? Just curious, was the VCE one? 3 marks, huh? Maybe he's older. So the more times I repeat, the less marks it's probably worth. So let's do another one. Now, next one, once again, so Insight is an institution in Victoria. Back in 2008, I had a question like this. Same concept. Can you see once again, right? Let me zoom in a bit more. The moment you see words like prove that MPN is a right angle. Now, where's MPN? This guy here, right? So for those with knowledge of circle geometry, which I'm a bit gutted that they removed it from year 11 and 12 syllabus, but you do it in year 10, or some schools do it in year 10. And we know that angles that subtend, in a circle, if you have a diameter, the angle that's subtended on the circumference is a right angle, right? Because that's the angle in the semicircle. So we know that, but now we've got to prove it using vectors. Great. So in this one, OP, right, is P. OM, where's OM? This one is M, which makes, now because this is a radius, right, this guy's also M, but also more importantly, right, because it's a radius, we know, right, the moment they define this, right, we know that the magnitudes are equal, and that is, once again, absolutely key, right? Because once the magnitudes are equal, they're asking me to prove this guy. So if I define, let's see, it doesn't matter which way the arrows go. If I define this guy NP, this guy PM, if I can prove that NP dot product with PM to be 0, I'm done. Yeah, I forgot to label the marks. I think it was 3 marks anyway. Exactly the same process. Guys, can you see 3 questions, different diagrams, same proof, same concept. In this one, it's implicit now. And just be clear to your teacher, right? When you write this blue one, just write equal radii, right, of a circle. Yeah. That's really the reason why. So instead of saying to you that the sides are equal, it's in a circle, so they're all radii, so it's all equal. So once again, let's define it. Now I can see it in the diagram. Let's see. I'll go NP first. So that's just M plus P, right? So NP diagrammatically, I can see M plus P. Brilliant. Now PM is equal to, what's that? See, it's going backwards on the P, forwards on the M, so minus P plus M. Guys, you always see 1 plus 1 minus, right? Because difference of 2 squares, the middle guys cancel out, right? But, yeah, and then you get difference of 2 squares, which in this case is the magnitude squared, difference. So bum. All right, let's go NP dot product with PM, right? I'm just going on automatic pilot, right? NP is this guy dot PM. By the way, some teachers are really pedantic about the tildes, right? The little squiggles on top, on the bottom of the vectors. Make sure you have it all there. Your teacher might be one of those that are, would potentially take marks off if you didn't have the tildes. I'll make it a habit of mine to try to do it, even as part of the working out. That's M minus PP. Go to the right bit, plus PM. Which, once again, if you're on autopilot, all right, these guys cancel out. Surprise, surprise, it's a difference in the magnitude squared. Because the magnitudes are equal, I can say this is like M minus M, which is 0. Boom. All right. Therefore, angle MPN is a right angle, guys. Right? Nothing hard about that. Hopefully 3 in a row, all different types of diagrams, same proof, right? So get that into your system, please. Next one. I'll do one more, right? Just to conclude this video on vector proofs, on geometric proofs. The next one, once again, isn't hard, but the concept is actually, I've actually butchered the next one. So I wanted to demonstrate a point. So the next one's from Canley-Val 2021. However, they had sort of 4 parts worth 5 marks in total. I basically skipped the 4 parts and I just gave you one question to give you what I think the question should be asking if it was made a bit harder, right? And I'll show you what I mean by that. So guys, this is a question from Canley-Val. It's a classic, yeah. Verignon's theorem, yeah. Now I have no idea how it's actually pronounced. Verignon theorem tells us that if you join the midpoints of any quadrilateral, the resulting quadrilateral, this pink one, so any quadrilaterals that are outside them, these are all the midpoints, the corners of the middle, the pink quadrilateral will be a parallelogram, right? Now, in Canley-Val, they then went on to define some vectors and then asked you ABCD to prove some stuff. I skipped that stuff and I basically said, can you please prove Verignon's theorem, right? So basically that EFGH, the pink, is a parallelogram. So I want to prove the middle is a parallelogram. Once again, putting our hats back on, flicking back to the front page, the best way to prove parallelogram is to prove that one pair of the opposite vectors is equal, right? So for example, if I can prove that this vector here is equal to this vector here, parallelogram, right? Because once you prove the vectors are equal, it's parallel and it's equal in length. Opposite sides are equal and parallel. That's a parallelogram. So let me just quickly write that down. So to prove this theorem, right, I'm essentially proving that HE equals to GF. So this is a different question. To nothing to do with right angles, right? So don't need that dot product thing. Instead, I need this, right? So let's look at what the question's giving me, right? It's telling me BA, that guy there, has a vector of U. AD has a vector of V. DC has a vector of W. And this guy has a vector of Z. Perfect. Now, why did they give me this statement, right? So why did they give me all these, all 4 of them? You guys know if I have a quadrilateral, any polygon, right? If you start off the vectors and you add them all and you get back to where you started, then the sum of all the vectors is 0 because you ended up directionally in the same place. So that blue basically is telling me this guy here, right? By defining all 4 sides to be U, V, W, Z, it's, you know, I started with the premise that the sum of all of these is 0. That's important because that's actually going to be my link to define what the greens are. So for all the greens, if you can see, right? So you know what? I'll leave it hanging for a bit. I'm going to put this statement up here and leave a gap because a gap is actually quite important, right? Why I need to, where I'm going to use this is actually quite important. So I'll leave that hanging for a bit. Now, what else do I know? The notion of midpoints, right? The notion of midpoints, where is it? Midpoints. So what that means is that, say, for example, right, this guy is equal to this guy, which makes, if I zoom in for a bit, which makes, where is my, let's go pink, right? Let's go pink. Which makes this guy half U, right? Because it's midpoint, right? And this guy to be half of V. And then I can use the 2 pinks and the green to get an expression for the green, right? So let's go there, right? Actually, I don't even need to draw it out. I'll just go HE. So from the diagram, now I've left a little bit of a gap here purposefully, right? So leave that there. Let's go down here, HE as a vector equals to half of U plus half of V, right? So if I can prove that the other green one is equal to half of U plus half of V, sweet, done, right? That's exactly where I'm going with this. So let's see. Let's see. Yep, so this pink as well. So this guy here is half of W. this guy here is half of Z. Yeah. So got H, right? That's a tick. So in this case, GF equals to, now GF is going up. Both of these are, it's almost like I've got to reverse both of these, right? So to do this, I'll reverse this one, make that a negative, reverse this one, make it a negative. So therefore it equals to, now it equals to minus half W minus half Z. And if you were smart about it, you factorize the negative half out. Maybe actually, can I ask a favor? I'll come back upstairs. I'll factorize a half from this guy as well. Just makes my algebra a bit cleaner, right? And then this one is W plus Z. All right. Now that you've done that, all right, got this, I need to prove that they are equivalent. Now you can see, right, that this one has U plus V, this one has W plus Z. Where's the connection? Upstairs, right? It all comes from upstairs. This guy here, the missing part. Now, let's go back up here. You can see then, if I threw these two over the fence and factorize them, right? I have actually what I wanted, right? See, with the negative down here, by proving this guy is true, I can prove that this is equal to negative of this, therefore they're equal, right? That is the actual key, right, to unlocking these two. So I can go, since U plus V equals to negative W plus Z, right? Therefore, HE equals to GF, right? Therefore, HE, no, let's do it in the order. EFGH is a parallelogram. Is that okay? So the blue thing upstairs, that where the sum of all the sides equal to 0 is actually the key, right? That's the thing that connects the two greens together, and hence for me to do this question, guys. So vector proofs starts off quite predictable and quite straightforward. Yeah. Next lesson, let's do a few more with ratio of sides, and then the third one, a few harder questions. Hope that was a good video for you. Not too hard, but good introductory video to vector proofs. Hope you enjoyed it. If you did, give me a like if you haven't already done so. I'll see you guys in the next video. See you later.